Welcome everyone. So today we'll be discussing lecture 8. So we'll be discussing product of symmetry operations. Product of symmetry operations. So we can also call the product as a combination of symmetry operations, because this is really not a product but a combination, because we are applying one symmetry operation after the other. So let's say if we are applying one symmetry operation first, followed by second symmetry operation, where x is one symmetry operation and y is the other one. So let's say if this is applied first and this is applied second, and the result of overall transformation of applying first and second symmetry operation can be directly achieved by a third symmetry operation, let's say call it as z, then we call it as that z is a combination of, so z is a combination of y and x. Okay, and the order of symmetry operation, the order of symmetry operations does matter here, because not all symmetry operations commute with each other. We have seen that earlier. What is a commutation of symmetry operations? So what I mean is yx is not necessarily equal to, it may or may not be equal to xy, right? Where this is your first and this is your second operand, and in this case x is your first and y is your second operand. So let's see, let's say if we have x1, y1, z1 is the coordinate of a given point in a coordinate system, and by operating with x we take it to x2, y2, z2, and again by operating with y we take it to x3, y3, z3. Then if you find a symmetry operation which can directly take you from x1, y1, z1 to x3, y3, z3 by using z, then z is called as combination of y and x in this particular order, right? Okay, so for example, let's say if we have we can say that if we have, this is one such example, two C2 axes perpendicular to each other, there exists a third C2 perpendicular to both. So we can say that let's say if C2x and C2y exist, because now they are both perpendicular to each other, C2z must exist. Okay, so let's say if we have, let's operate this C2x on xyz. So operating C2x operating on xyz. So in this case, let's see what happens if we have right-handed coordinate system. We have x, y, z, and now if my C2 is running along x-axis, this is my C2, okay, anti-clockwise direction. So what happens? So y will go to minus y, z will move to minus z, x will remain as same, because x is not moving, x is lying along the x axis, right? So what happens? My coordinates will change, like x will remain as such, y will go to minus y. I am representing minus y as y bar. Z will go to minus z, right? Now similarly, if I am applying C2y, what happens now? So x goes to minus x now, minus y remains as minus y, and minus z goes to plus z. So I hope this is very clear. So what I have done here is, now I have used C2 y axis, so y remains where it was and x and z change their sign. Okay, so now you can easily see that if we have to go from here to here, x is changing its sign, y is changing its sign, whereas z is remaining as such, which can be obtained by C2 z operation, right? So thus we have shown that if there are two perpendicular C2 axes, there must exist a C2 axis which is perpendicular to both. So now C2z is perpendicular to both x as well as y, right? So this is called as product or combination of symmetry operations. So that means we can say that existence of two symmetry elements may automatically require third one to exist. So for example, here we have seen that C2x and C2y were existing, and because their presence is there, so C2z must exist. So that means it's the existence of C2x and C2y is directing the existence of C2z, right? In other words, we can say the combination of two symmetry elements we can say operations actually is itself an operation, right? So let us take an example to see, and the order does matter. We will see in certain cases it may commute, in certain cases it may not commute. So let's take an example. So BF3, let's say 1 2 3. Okay, now let's do an operation. We know that there is a C3 axis here, right? C3 axis is lying, passing through B and lying perpendicular to the plane of this board. So if we do a C3 operation anti-clockwise, what happens? It will change, the B remains at its own position, and then 1 moves here, 2 moves there, 120-degree rotation, 3 moves here, right? Now let's say if we do C3 square operation, okay, so C3 done twice onto this. So what will happen? Now my 3 goes 2 times. 3 will move 1, 2 because C3 is done twice. So in one C3 it will go from here to here, but we are doing C3 twice, so it should move like this. So it will be a 240-degree, 240, right? Yeah, 240-degree rotation. Okay, so C3 goes here, F2 comes here, F1 goes here. Okay, so let's see, we have 3 here, 2 here, 1 here. So this should be very clear. Now if you see, if we have to go from here to here, what will be that operation? Now look at the atom position. So F does not change, F1, F2 does not change, F3 does not change. That means this operation is nothing but a identity operation. So we can say that C3 and C3 square. So remember the order we have used here is C3 is operated first and C3 square is operated second. Although in this case it does not matter, we'll see why. Is equal to E, right? So whenever two symmetry operations combine to give, so we can say that when two symmetry operations combine to give E, we say that one operation is inverse of the other. We'll see what it means. So we can say that C3 is equal to C3 square inverse, or C3 square is equal to C3 inverse. So what do I mean by inverse? So inverse is doing the same thing in the opposite direction. For example, if I'm doing C3 anti-clockwise and C3 square clockwise, so it would mean the same thing. So it's like doing the same thing but in opposite direction. So if I'm doing C3 square, then it will be equal to C3 inverse, right? So okay, let's see that again. So BF 1, 2, 3. So if I'm doing C3, then what do I get? F2, F3, F1. And now if I'm doing C3 inverse, then that will be doing the same operation but in the other side, right? So what do I get? So I get the same thing back. So 3 goes back, 2 goes back, and 1 goes back. So now you see that we have done C3, C3 inverse, and I'm getting the same as we got after doing identity or C3, C3 square. So that means now C3 square becomes equal to C3 inverse, right? So these two operations, because now the first set of operations are same, C3, C3, and the second set of operation here was C3 square, whereas here it is C3 inverse, but the resultant is same. So we can safely say that C3 inverse is equal to C3 square, and you can also do the vice versa thing. So basically it proves that when two symmetry operations combine to give you E, we say that one operation is inverse of the other. So that should be easy. But okay, so now let's also see a case where the symmetry operations do not commute. So in this particular case, actually, let me go back. The order does not matter. So we can say that C3 and C3 square, if you do it, then also it will be equal to E. Okay. So order does not matter. Order independent. Because they are combining to give E, the order would not matter here. But if they don't combine to give E, the order will matter and it may or may not commute. Okay, so let's look at the same molecule again and take a combination of two different symmetry operations. So let's again do C3 first. So we have 3, 1, 2, right? 1, 2, 3, yeah. Now let's do sigma V1. So sigma V1 will be this plane. Okay, so the plane which is passing through BF1 in the original molecule, not in the transformed molecule. So the location of this sigma V1 will be with respect to when we started with the molecule, not where we ended after doing the C3 operation. So that has to be very, very clear that whenever we are taking the initial configuration of molecule, we are fixing all the symmetry elements, and accordingly we have to take the symmetry operations. We can't be moving symmetry. So for example, if we say that this is my location of sigma V1, that would be incorrect. So this is not sigma V1. Okay, my sigma V1 will be this one. Okay, so then in this case my sigma V1 will be this. This should be clear. So if I do this operation, then what do I get? So that means F3 does not move, and the two F's will be reflected, the other two F's, F1 and F2. Okay, so now if I have to go from here to here directly, what will be my operation? So in this case, if you see that F1 moves clockwise to this, then F3, basically F2 does not change, and F1 and F3 are reflected, right? That means if I reflect it by sigma V2, this will be the operation which will take it from first to, let's say if we call it first, second, third. So we can safely say that sigma V2 is equal to sigma V1 C3. So the order is we operated C3 first and sigma V1 second. Okay, now let's see what happens if we do it reverse. So let's take the same starting point, BF3, F1, F2. I'm doing sigma V1 first. So what do I get? So again, my sigma V1 position is, this is my sigma V1. So that means the F1 does not move, F2 and F3 will get reflected. Now if I do C3 operation, what do I get? So if I do C3 operation, 1 goes here anti-clockwise, 3 and 2. Now what is this operation? So in this case, my F3 is not moving, F1 and F2 are getting reflected. So I'm comparing 4, 5 and 6. Okay, so in this case, if you see F3 is same, whereas F1 and F2 are getting reflected. So that would be sigma V3, right? So in this case, if we change the order, what do I get? C3 sigma V1 is equal to sigma V3. So you see how the this particular product, if I change the order, it results into two different symmetry operations. So we can safely say that C3 and sigma V1 commutator is not equal to 0, right? So they do not commute. Is that clear? Okay. So C3, or we can say C3 does not commute with sigma V1, right? Another important property symmetry operations follow is symmetry operations obey associative law. So what is associative law? Associative law means that if we have two operations x, y and a third operation z, then x, y product of two operations into a third operation is equal to x, y, z. So what do I mean in this case? So I mean that if I am doing this operation first, and then the combination of this as second, this will be equal to, if I do combination of this as first and this as second, okay, this should be equal always, irrespective of what molecule is, what the symmetry operation is, and so on. So right, so this should be very clear. So symmetry operations obey associative law, and we can test it out using any example like BF3. So take it as a home assignment to verify associative law in BF3 and H2O. So let's take two different examples so that the operations, how to do these operations, will be very, very clear. Okay, and come back to me if there is any issue with this. Okay, so let's now take, so we are now ready to actually go to define what is a point group. So let's take the example of symmetry point group. So what is a symmetry point group? So by definition, a complete set, we will see what is a complete set. A complete set of non-redundant symmetry operations. So I'm saying symmetry operations and not symmetry elements, thus identifying the list of symmetry operations is crucial. Okay, so we have learned how to first list down the symmetry elements and then find out what all non-redundant symmetry operations exist. So a complete set of non-redundant symmetry operations, and I will specifically write here, and not elements of a given molecule defines a symmetry point group. We'll see why it is called as point group and all. Okay, so for example, if we take example of water molecule, the symmetry elements and thus the operations, so we'll list out both. We have seen this earlier. So elements are E, C2, sigma V1 and sigma V2, right? And the corresponding operations are E, C2, C2 square will be equal to E, so we'll not consider that. Sigma V1 will generate 1, sigma V2 will generate 1, right? So this forms a point group called as C2V. Okay, so we define it as C2V. This is the notation we will learn later called as Schoenflies symbols of point group, but let's see. So these set of symmetry operations, not the elements, this set of symmetry operations will give you point group as C2V. And now let's look at another molecule, cyclohexane in boat form. If you have done this exercise, so here also the elements are E, C2, sigma V1, sigma V2. So this I give it as home exercise to identify the symmetry elements and operations. So this is very similar as water. So although the water and cyclohexane boat form, they look very different, but their symmetry operations which are existing in this are same, and hence both of them belong to C2V point group. So that means any physical property which is dependent on the symmetry operations, because of this classification, they will be sharing those physical properties, right? So it is interesting that how the two differently looking molecules are classified into same category because they have same set of symmetry operations, and thus their physical properties will be very similar. Whatever physical property depends on this set of symmetry operations, right? Okay, so now let's see how to determine this point group and what are different types. We'll see that. How to determine symmetry point group of a molecule. Okay, so let's look at this. So first thing here is to inspect all the symmetry elements in the molecule, right? Second is list down the operations generated by the elements listed in the above step, elements in step 1. So up to this we have seen how to do this, right? But this is not so easy because in certain cases where the molecule is big and highly symmetric, the number of operations are huge, and then sometimes we may miss out one element or the other, and unless we really practice it hard. So you'll find several books have flowcharts made, can be followed to find the point group. So we'll see how. Okay. So, but before we go there, let us see what is the complete set, right? What is the complete? What do I mean by complete set of symmetry operations? So, a complete set is a one in which every possible combination of two operations in the set is also an operation in the set. So this may sound confusing, but let's see. So what I'm saying is that if we have, let's say, if we define a group where the set of symmetry operations are A, B, C, D, and so on, then if we combine two symmetry operations in any possible way and we get, let's say, C, or if we are doing BA, we are getting D, then C and D must form the element of this group. Okay, so that will define the complete set. Similarly, if we do AC, we should have another product which should form a part of this set. So this way, this is called as a complete set. So again, so let's take an example. So again, let's take the same BF3 case we have been discussing. So in this case, the symmetry operations, let us list it down: E, C3, C3 square, then we have C2, C2 prime, C2 double prime. So I'm not writing it as 3C2 just so that we are listing all the symmetry operations independently, but they'll be essentially equivalent, so we can actually say 3C2. But let's see explicitly listing all the symmetry operations. So we have sigma v1, sigma v2, or we can call it as sigma v prime, sigma v double prime, sigma v3, and we also have sigma h. So now if you see C3 and sigma h is there, then S3 would also exist. So S3 square, right? So now if we say that if we try to take a product, so this is a complete set of symmetry operations for this particular molecule. Now if we take product of any two symmetry operations or combination of any two symmetry operations, it should give rise to a symmetry operation which is already present in this set. Okay, if it is not, then we must include that operation also into this set. Okay, otherwise it will never be complete. So what I mean is that if I'm combining, let's say C3, and then I'm doing a sigma v1, we have seen this earlier. If we do this in this order, what we get is sigma v3, right? So now we are combining C3 and sigma v1, and what we are getting is sigma v3, which is already present in this group. So similarly, you should be able to test out. So take it as a home assignment number 2 for today, to verify that the above set of symmetry operations is a complete set. Okay, so by complete set I mean that any combination of two symmetry operations should give rise to third symmetry operation, which must be present within this set. So you should be able to verify this. And the combination is not necessarily that two symmetry operations have to combine. It may also be the case that C3 and C3 are combining. For example, if we combine C3 and C3, we will get C3 square. If we combine C3 and C3 square, we will get E. So I have already done at least 3 combinations for you, so you should be able to verify how to do this. Okay, so that's it for today, and next class we will look at how exactly we find out what are the properties which are required to form a symmetry point group, and how do we find out symmetry point groups. Okay, all right, that's it for today.